Coach Johnson coming to you live. This is AP Stats Chapter 3. Can't believe it. We are rocking and rolling here together. Oh, why not? Let's just shoot it again. Oh, I did it again. Oh, my goodness. 2 for 2. Yeah. Man, it's going to be a good day. It's going to be a great podcast. I might just teach like this. Just the heck. What the heck, you know? Man, I just made it again. Back-to-back nights. Man, this is getting better. I'm practicing something, you know? Hope you're having a good day today. I see we got 1 viewer. I know that's going to probably increase here shortly, but let's do this. Let's get straight to our FRQ here. Little goofy movie music to get us started. If you haven't seen that movie, good night. Great movie. Great movie. As I go through this, one of the things that I'll encourage you to do, please text me, message me, message on the YouTube channel. Give me a 5-star rating right there. Thank you. Also, yeah, I always have to mention my followers from Sweden. They are always very friendly and show up to all my podcasts. So without further ado, let's get started. I hope that maybe you at least got a chance to just to take a little peek at this FRQ here. Maybe you did the other one, which is A-OK. But let's take a look at it. Let's see what the answers are. And then I'll go through just the way that it's graded, and we'll go from there, okay? Here's what I would recommend. If you have not done this FRQ, I would recommend before you listen to this that you would go to this FRQ, maybe even do this right here. It's this one and this one. I believe it's on online. Check it out. I'm trying to get a lot of FRQ practice for you, and so let's go from there, okay? And what I'm going to do is, Coach Jay, I have not seen any of the answers, by the way. I did copy them, but I've not seen any of the answers. So let's see what Coach Jay did on this FRQ, and then we'll go from there, okay? All right, let's talk about this. 2 statistics students. By the way, each of these should take about 12 minutes, okay? Like if I give you an FRQ, each of the FRQs should take about 12 minutes there. All right, students went to a flower shop, randomly selected 12 carnations. When they got home, students prepared 12 vases with the same amount of water. They put 1 tablespoon of sugar in 3 vases, 2 tablespoons of sugar in 3 vases, and so on and so forth. In the remaining 3 vases, they put no sugar. After the vases were prepared, the students randomly assigned 1 carnation to each vase, observed how many hours each flower continued to look fresh. Okay. A scatter plot of the data is shown below. So the explanatory is this sugar, and the response is my freshness here, okay? It says, briefly describe the association shown in the scatter plot. Well, if it says describe, I'm going straight to DOFs, okay? So I want direction. So I'm going to say, I'm just going to put this here, a positive. I'm going to skip outliers for a second. Positive linear. And I would say, yeah, relatively strong, positive linear correlation, okay? So I'm going to hold off on that and just label this here. And I'm also going to say that it has with no outliers. Now, I know right now I'm missing context, but I like to answer the question first and then approach it from the back end and say, okay, let's provide some context. So when, and so if this is sugar is the explanatory, freshness is the response, all right? So we would say when looking at, I'm going to keep going up here so I can kind of write in here, and this would follow at the end. When looking at the correlation, sugar, or tablespoons of sugar, has on the freshness of a carnation we found the LSRL to be relatively strong positive linear correlation, or to be a relatively strong with no outliers. That right there is pretty doggone good. When, again, we're looking at the correlation the sugar has on the freshness of a carnation, here's what I would say Is there anything else I could include? I would probably add, if I had some time, that this was the explanatory in parentheses. And I'll put that in parentheses. And then that this was the freshness was the response, okay? And I would put that there. Okay, so let's see if Coach Jay got it right. Okay, it is essentially correct. Okay, so again, when I grade these, I'm looking for different parts on the rubric, okay? So just a heads up. It says it's essentially correct if the response correctly addresses the direction, I did, the form, and the strength of the association in context. And I did that. So guess what? I got an E on this part. Again, I don't do it quite like that. I do, I'll go through the rubric and say check, 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 check. I give it a little bit more grace on this, but that's what I'm looking at when I'm grading. So just a heads up there. When I'm going. It says the equation of the least squares regression line for this data is interpret the slope of the line in the context of the study, okay? So I would go about it the same way. So I would say, let's say first 15.8, okay? So I'm going to put this over here, 15 over 8, or 15.8 over 1. That's y over x, correct? And what is y? Y is the freshness of the flour, okay? And X is the sugar, okay? So look, I outlined it real quick, just outlined it really, really fast there. And then what I would say is this, and corresponding to this, I would say when looking at the correlation, I'm referring to the correlation regarding the impact, when looking at the correlation, I always have to kind of rewrite this. When looking at the correlation and how, I like that, we can go straight to it, and how sugar impacts the freshness of the carnation, okay, we'll just do this here. The slope of the LSRL, least squared regression line, was found to be 15.8, okay, which means that there is, again, this is freshness in days, right, okay, that there is 15.8 days predicted for the flour to, I want to make sure, be fresh per 1 tablespoon of sugar. Now, let me tell you what I could take out. Because I established the overall context of this problem, I could actually take out, if I look at, let me go over here. Okay, if I look at this part right here, when looking at this part, I could go straight into the slope, okay? That does right here all the way through. That's all I needed because I already established this in part A, okay? So just a heads up there. So as I look at it, all right, so it's essentially correct if the response describes the predicted, expected, or average change, right? I said predicted, found to be, which means that they're 15.8 days predicted. Okay, that's huge. So you could have said expected. You could have said average change in freshness time for each increase of 1 tablespoon of sugar, okay? Predicted for the flour to be fresh per 1 tablespoon of sugar. I probably could have included, this could be borderline to say increase, but I guess here you'll see that if I didn't say predicted, reverse the roles of the variable, use the wrong value for the slope, so on and so forth, doesn't answer in context. That right there, again, will knock me down to a P level, okay? So right now, I think I would give myself an E on that. I think I hit all parts on that part. I didn't say increase, but it was assumed on that, so I'll give that to myself. All right, let's look at the next part. This is C. This is our last part that I've got. I'm sure, I think there's part D. You could take a look at that. It says, calculate and interpret the residual for the flour that had 2 tablespoons of sugar and looked fresh for 204 hours. Okay, So let's talk about this. First off, let's put down what formula we know. Y minus y hat equals my residual, okay? That's very important. It's also important that when they give this to me, that we already know, we label what we know. So it looked fresh for 204 hours. So that's actually, it's my actual, okay? So my actual is 204 hours, okay? That's there. What I'm trying to do is find what is y hat, right? So when I do that, I could plug in for the equation. Now it doesn't say, oh, it does say interpret there, okay? And so that I need to interpret this. But just so we're clear, I would plug this into the formula, and I would actually do this below. I would say y hat equals, and I'd show this just in case, plus 15.8 times 204. Oh, I'm sorry, that's incorrect, because that's my y, right? I'm looking at the x, which was my explanatory for 2. So I would say 2 times 15.8, okay? Get 31.6, and then I would add 180.8 to the end to get 212.4, okay? So this is the predicted, this is my actual, and I would show this right here, right, to show that it leads to here. And so I would say 204 minus 212.4 equals negative 8.4, okay? So my residual is negative 8.4. Now, interpreting this, I would say the following, and again, I don't know the answer, so you might be able to kind of critique me here. I would say, I already established the original context before, right? So in interpreting the residual, yeah, I would go right straight to it. In interpreting the residual, I would kind of state this question right here. For the flour, we saw I would say the predicted value was, and then fill in the blank, okay? Well, let's do this. Let's actually talk about what we just did. So let's go, in interpreting the residual for the flour, the predicted value was subtracted from the actual value to get the residual of the flour's freshness or something along those lines. Now, I might have points counted off. Let's see what they have here. Again, I'm just answering it the best I know how. I went straight into it. Let's see if they count it here, okay? Let's see. It's essentially correct if the response includes the following 2 components: correct calculation of the residual with work shown, boom, correct interpretation of the calculated residual in context, including direction, okay? Well, you know what? I would probably count myself off if I were to get one. I would take maybe -1 right here, because I did not include the direction. Because I excluded this, right? I should have said in context a little bit better. This is 8.4, so negative 8.4. I would say 8.4, because of this. This is 8.4 hours below the predicted value. I think that would be somewhere including this in here below, something along those lines. That's how I could correctly interpret that. So I would add this to your analysis. I would have gotten, this is what I would have gotten. I would have gotten an E here. I would have gotten a P here. I would have gotten an E on this first one. So I would have gotten an EEP, which is a 3 out of a total 4. Okay, you probably, some of you, Matt's been tearing up in class. I love it. I love a lot of y'all. Y'all are rolling. Y'all probably got 4s on that, which is awesome. But hopefully that helped there, going through some of those questions together. I'm going to go on let's see here. Perfect. Can you do homework problems 61 and 72? I can do that. Yeah, let's do that. Let's open up with those, and then we'll go straight into the other stuff here. I've got my textbook here. We're rolling. Hit the shot. Man, this is a great day today, and hopefully this is helpful for you. giving you some ideas of what's on the test, what can we study, and what can we do going from there, okay? So let's talk about real quick, actually, before I do that, let me just touch base on this, and I'm going to just include a page before the current here. I want to just tell you a couple things. First of all, we just interpreted what the residual was, right? The next thing is that I want to interpret is this R, the R, right? We call that the correlation coefficient, right? And when we talk about the correlation coefficient, we can go into DOFs, okay? So if this thing is 0.84, right, we could use DOFs to be able to analyze it. You'll notice we can use DOFs when we talk about R, when we say interpret R. We also use DOFs when we said briefly describe the association within the scatter plot, right? So that's what we're talking about in terms of this here, okay? Now, as far as the other ones go, remember, again, these were the areas that I highlighted before, right? So this is with R. We talked about slope interpretation. We rocked that. Really, the residual, that's the one I needed to work on just a little bit, okay? So there's that. And then the slope and then the y-intercept, right? The y-intercept, just be careful on that. For instance, on this previous one, if you were to go to this right here, we would say 180.8, right? And really, this is 0, 180.8. So when we talk about this, we would actually describe it as when the x is 0, the y is 180.8. And in context, we could say, because the explanatory, I want to make sure I was right. Yeah, when the explanatory was sugar, we would say that we can expect that a carnation with 0 tablespoons of sugar would stay fresh for approximately, that's a key word, that ly word softens it, or it's predicted, that's probably the better word, it's predicted to be fresh 180.8 days, okay? Because of the fact that this is the y-intercept. So y-intercept and slope, we just tackled those together. We remember too the, and I'm going to get to the hard one in a second, that's why I'm waiting. We remember that if this is the x, whatever the explanatory variable is, so over here this could be tablespoons, right? And we said that if there's a dot plot, right, and there's equal number of values and it's kind of scattered, we'd say the least squared regression line would be a good interpretation of this. We also stated that in a residual plot that we've got to be really, really careful because for, let's say for some reason we're, let's say if in this we have, and I know I'm going all over the place, sorry about that, but let's say we had some sort of pattern. If it follows some sort of pattern, we would say the least squared regression line may not, okay, we're not going to say it isn't, but it may not be a good interpretation of the data that we have at hand, okay? Now, let's talk about this, the R squared, okay? I want you to get to R squared, and Campbell, I have not forgotten about you, but I want to hit these before I go any further. The R squared is called the coefficient of determination, okay? Coefficient of determination. Now, what is it? Well, we're talking about the variation, right? The key word is when I see variation. There's one on one of these. In fact, I think there's an actual definition for this. Let me see here. I'm going through. I got one. I thought I had one earlier today. Sorry about this. I just want to make sure, see if I can get one here. Oh, right here. So what percent? It's the percent of variation, okay? It's the percent of variation that can be explained from y, the relationship of y on x. So what the heck does that mean? I had something here. Okay, I'm going to read you the definition here. It's the coefficient of determination, R squared, is the fraction of the variation. Okay, variation is like, remember, if I vary, right? Standard deviation is like variance, right? So if I if I have variation, that means it's more spread out, right? The higher percentage of this R squared, right? Let's say that R squared was like 96%, because that's usually where it's at. That means that that's a pretty good variation on this in this example. So again, let me read it again. R squared is the fraction of the variation and the values of y that is accounted for by the least square regression line of y on x. Let me say that again. the fraction of the variation in the values of y that is accounted for by the least squares regression line of y on x. Maybe the formula will help us. This is not something you need to know. You can do this all by hand. But in order to find this, we take the sum of our residual squared, right? Okay? Take the sum of this residual squared, okay? And we divide it by the sum of the y value, each y value, subtracted from its mean, squared. So again, what this means is that the higher the percentage, the higher likelihood, not cause and effect. I want to make sure of that, okay? This is not a cause and effect thing. But the variation of the actual data points, what does that mean? That means these data points are a lot tighter together. And what this means is that the least squares regression line, the higher the percentage, the least squares regression line is a better indicator that there's a correlation of y on x. Again, it's very similar to R, is it not? R is standing for DOFs, right? We're talking in terms of that. But what we're saying is that the variation, okay, in greed, in this way, what is greed? Well, greed would be the values of y, right? Okay. This would be the response. So the variation of the response explained by the relationship with that, whatever that superciliousness word, okay? So I hope that makes sense. Even as I say it right now, I understand that, okay, maybe this will help because as I'm talking about this, if you ever say something and you're like, it needs to be better. Okay, here's the definition, and this is taking an example from the book in terms of, okay, so this is what it's talking about. Okay, this is the price of the car, and this is miles driven. I think we talked about this one at one point. So if the miles driven increases, what happens to the price? Well, the price will decrease. Okay, and for this right here, the R value. I'm trying to see if it gives us the R value. I don't think it gives us the R value here, but that's okay. What it does say is that the R squared value is 66.4%. And here's how they interpret it, okay? With this scatter plot, they say this. 66.4% of the variation, we always start with that one with R squared, okay? Of the variation in what? Of the variation in our Y. So of the variation in price, okay? So like variation, as the price varies, 66.4% of this, the variability or the variance in price, okay, is accounted. So it is accounted for by the linear model or the least squared regression line, okay? So 66.4, I'm breaking this down for us with the model. 66.4% of these variances within price is accounted for by our linear model or our least squared regression line, okay? All right, I think it has one more thing here. Relating to miles driven. I hope that makes a lot more sense. So what does that mean? Of the variation as the price varies, right? This variance, 66.4% of this variation is accounted for. Doesn't mean it falls on, but we can expect it to be falling. And again, if it was really wide out here, right, there were dots out here, that means this would decrease, right? The variation would decrease. But the tighter they are, the higher the percentage. So of the variation in price is accounted for by this linear model relating to the explanatory or our miles driven. I like that response better, and I like that explanation better. My apology for kind of going around all over the place, but I hope that was worth your money. This right here is a good interpretation for R squared if you need that for tomorrow, okay? Excellent. Okay, sweet. Hopefully I didn't confuse you too much there. Sorry, sometimes I have to kind of go around it and then nail it, and I think I just nailed that there. Okay, if you have more questions about that, we can do an example tomorrow to be able to help you interpret that even more. The only other thing before I get to Campbell's question, and Campbell, I do promise I'm going to get there, is this mini tab. All I would say is that when you go to this mini tab here, I think I skipped it. When you go to the mini tab, just please be careful. Please be careful. You don't just kind of skip it, right? So just remember that this right here, the constant, is the value that's by itself, right? So this is, if we were talking y hat equals ax plus b, the constant, the b, is the value by itself, right? I'm sorry, this right here. So this right here, that value is b, where the explanatory, which is h, okay, that's why it kind of goes here, would be the a value, right? This would be the slope. The SE coefficient, T and P, we haven't done yet. R squared, ADJ, we haven't done. Here's the standard deviation right here of the residuals, and here's the residual squared. So just be sure, if I give you R squared, just make sure you square root that 0.41 to get a value between 1 and -1 for my R, if I asked for what the correlation was, okay? So again, Campbell, sorry about that, but I wanted to make sure I hit on some of those before we went any further. Okay. Now we're good. Let's go to number 61. Hit on a lot of stuff there. Let's go to 61. Says this. Wow, this is a good one. The mean height of married American women in their early 20s, okay, is 64.5 inches. Standard deviation is 2.5, okay? So let's go. Let's talk that through, okay? So the mean of the women height, okay? Women's height, okay? So this is, we'll say this is X, right? So X bar, which is our mean, equals 64.5. This is a good one right here. Standard deviation of X, right, is going to be 2.5 inches, okay? 64.5. That means the mean average height of women is taller than me. Just let that sink in. I know you're laughing right now. I don't appreciate it, okay? I am not small. I'm fun size, okay? I am fun size, all right? So if I ever hear Coach J small, Coach J short, ha ha, Coach J, look at him, I'm going to be upset. Fun size, I prefer. Thank you very much. So with that being said, the woman's height's there, okay? Then goes on to say the mean height of married men, okay? So this is married men. Oh, this is married women too, but we'll just put men height this is Y, right? The mean height for men is 68.5, okay? I'm only 6 inches off. We're good. And the standard deviation of Y is a total value of 2.7. Okay, so I just like to write it down because it helps here. So then it says the correlation between the heights of husbands and wives is R equals 0.5, okay? The only thing that I would say here is the correlation between the heights of husbands, mean height of married men. Find the equation. Okay, so R equals 0.5, okay? Again, remember, this does not, we don't know what the explanatory and response is, but we don't have to know with at least this first part, okay? Now, question A states, find the equation of the least squared regression line, which is y hat equals ax plus b, okay? Trying to find that. Notice, by the way, how I'm not perfect at this, but one thing I learned in taking a test, whether it's college, AP, or whatever, is just as I go step by step, is just writing what I know down, okay? I can't ever get counted off for showing more work than I need to. It says, find this LSRL, least squared regression line, predicting a husband's height from his wife's height. So when given the wife's height, so I was actually right here, this is the explanatory, okay? And this will predict the response of our men's height, okay? All right, hold on just a second, y'all. I think someone, hold on just a second. Gotcha. Sorry about that. I had my, we have this camera for my daughter's room, and right now I just realized it was not on and not with me. So that's a problem. But I think she's okay there. So what we're gonna keeping going, it says predict or just come up with the equation of the least squared regression line in their early 20s. Find the equation of the least squares regression line and predict a husband's height from his wife's height for married couples in their early 20s. Well, we know, as I go, so yeah, so I would say Okay. Are these okay? This whole thing is from the early 20s. Okay, I was confused on that. All right, so come to this part here, and we actually did this today. We to find the slope and to find the y-intercept, we're going to use these right here. Okay. By the way, while I've got you here on this topic, remember the one in class about this right here that I was like extremely confused on, at least with 7th period. This should have a bar over top of that one and this one, which would make this one extremely easy, and it wouldn't be very bad and would be very similar to the one we're doing right now. So that should have had a bar on it, and for some reason there was a typo on it, and so that was the problem. But it should be that way. That's how it was on the AP exam. So to find the A and B, we're going to approach it this way. I think they switched A and B, which is okay. I'm not too worried about that. So what I'm going to do is just kind of, in coming here, I'm going to say that the A is the slope. That's what we have right now. If you change it up, that's A-okay. That's fine. But we're going to do the correlation, which is R, times the standard deviation of Y over the standard deviation of X. So we're going to say 0.5 times the standard deviation of I want to make sure I've got it right, Y over standard deviation of X, okay? So we're going to do the 2.7 over 2.5. So I'm going to do 2.7 divided by 2.5. And then I'm going to multiply that value by 0.5. And when I do, I get 0.54. At least that's what I got here. So 0.54 is A. So Y hat, the predicted value, equals 0.54 X. And then to find my B, well, one thing, well, let's just keep going because I think it ends up building into there. Y, the mean of Y minus B, okay, so the mean of Y right here, 68.5 minus B, which was, or my A, it really was my slope, 0.54 times my X bar, so 64.5, okay? So we'll do 64.5 times my 0.54, okay? And I would then subtract that from 68.5. So I got 33.67 or 33.7, either way. And we would go from there. Now, the only thing that I have a question on is the slope. We've got to think logically whether the slope is positive or negative. Here's the woman's height, right? As the woman's height increases, what happens to the height of the male? Well, I would say that would increase too, right? So if the wife's height increases, you probably would see this gradually increase as well. But maybe that's right, maybe that's wrong. But that's where we're at here. Okay. So that's for A. For part B, and oh, by the way, in context, I keep putting this and this. I would highly recommend for this Y hat, I would put men's height, men's height with the hat on it, and then X put women's height. And you don't put a hat on that because the X is the explanatory, that's set in stone, but the predicted value varies based upon your explanatory. Okay. All right. I don't see any other questions here. I see 7 viewers out there watching, so good stuff. Keep that up. Let's take a look at B. B says, suppose that the height of a randomly selected wife was 1 standard deviation below average. Predict the height of her husband without using the least squares line. Okay. Wow, that's a really, really good one. Well, we remember, does it say it's normal? The mean height doesn't say that it's a normal there. Suppose that the height of a randomly selected wife was 1 standard deviation below average. Doesn't say. Does it say? I don't see that it's a normal distribution. Well, I'm going to assume normality. Okay, I'm going to assume normality here. We're going to assume that it's going to be approximate, okay? So we know the mean here for the woman, right? Because that's what they're looking at, 64.5. If she is 1 standard deviation below, so we're going to subtract 1 standard deviation, which our standard deviation was 2.5. So if I did that, 2.5 subtracted from 64.5 would equal 62. So the predicted, or I'm sorry, the expected, backtrack. the height of the woman is 62 inches when it's 1 standard deviation below the mean, right? Okay. And I don't even think that it necessarily has to be normal for me to subtract 2.5 here. I'm just going to do it just to show you because it links to chapter 2 here. But regardless, because this is 2.5 inches and that's 1 standard deviation below, we'd subtract it to get 62. So if I were to predict what is the height of the male, if the female, the explanatory, was 62, we could plug 62 in for this equation, multiply it by 0.54, and add 33 to get what that expected, or the predicted, okay? I keep saying expected, that's incorrect. The predicted, the y hat predicted value, that's there, okay? Number 72, let's get that one there. Each year, students in an elementary school take a standardized math test at the end of the school year. For a class of 4th graders, the average score was with standard deviation. The 3rd grade, students had average, the correlation. Okay, here's the deal. All right, Campbell. All right, here's what I want. All right, so Campbell, here's what I want. I'm actually typing you. Hey, does this make sense now? Does 72 make sense now? I put it in just so that people who are coming in late can see. I hope that 72 makes a lot more sense to you because you'll just go through and do exactly what we just did. You'll go through and as you plug in the values for what your slope and what your y-intercept is, you should be able to get what the answer would be there for 72. Butamus, awesome. Okay, so hopefully we're still good there. Make sure I'm all right. Can y'all see me still? I hope y'all can still see me on that. Right now I have it's showing my screen is down. Is my screen down? I want to make sure. Can y'all see me pretty good? I want to make sure, kind of give a second there. Just someone throw in the chat that everything's good, just in case, so that I can keep going. I'm going to go to the multiple choice section here now and want to make sure we're all good. So again, if you're about ready to do the multiple choice section, and perfect, thank you. For me, it's showing me that I'm down for some reason. What I'd like to do now is kind of go through each of these, kind of give the train of thought here when going through each of these problems. We'll go through as many as we can in about 20 minutes. I'm recognizing tonight this podcast is going to be longer, but care for you. I love you guys. And I really do. I really feel like we can do well on this test. I really, really do. And maybe I hope you feel the same. Throwing out a lot of work, a lot of things, and a lot of context is huge. All right. So just so you know, like when you take a test, right, it's important to note that 12 minutes, those two are for FRQs, okay? That's how we balance it out. Now, with these 10 multiple choice, some of you crank those 10 multiple choice questions out, and some of you could do it within 15 minutes, okay? Some of you actually will do this in 15 minutes with a 10 multiple choice. So that would be 12, 12, 24 plus 15 is like 39, right? So I would say that on average, 1 minute a question on these are pretty standard, okay? A minute to a minute and a half, depending upon the length of it. If you look at this one right here, you'll notice that like which one is true. This one you probably could do in like 45 seconds. It says correlation and regression require explanatory and response variables. This one we looked at in class. This is actually true. What you don't have to have in correlation, you don't actually have to say one variable is explanatory and one is response. However, it does still require one explanatory and one response on there, okay? So Alan, if you're watching this, I hope that makes sense because as I went back through it, it requires that you have both of them, but as far as the order goes, that doesn't matter with correlation. Remember, correlation coefficients here, R squared is the coefficient of determination, right? Okay, keep us going. Scatter plots require that both variables are quantitative. That is true. Every least squared regression line passes through X bar and Y bar. These are all true, and that's why D is my answer. Now with A, some people were going through this one today. The one that we were really looking at, I think the one that we were really focused in on was the difference between A and E. Remember when we're talking about the slope is approximately 9, right? And that's rise over run, 1 run. And again, remember we talked about this in interpreting the slope. This means that 10 is related to the Y, or the response, which is calories. So for every, really, let's start with X. For every 1 increase, actually, let's start at the top. My fault. I said at the bottom. My fault. As we increase the breakfast cereal by 10 calories, we can expect the cereal to also, we can predict, not expect, keep saying expect, it's predicted. Predict, okay? We predict that there will be 1 gram, is it gram of fat, amount of fat, however you want to say it, within that cereal for each additional gram of fat, in that cereal. They flip-flop this a little bit, but A would actually still be correct. And the one that's incorrect is this one, because if one cereal has 140 calories, okay, and 5 grams of fat, okay, it says the residual is about 5 calories. Well, if you plug 5 into the fat to see what the, like this right here is the, like this right here is the expected, right here, the expected value. And the predicted value is when I plug 5 in for the fat. And when I get that out, I would get 145. But the equation is y minus y hat, which would produce 140 minus 145, which is -5, okay? So y minus y hat is -5, so that's why this residual would be the one that would be incorrect there, okay? All right, I'm just going to keep looking right here. Good. All right, Sweden followers, hopefully you're doing well here. Matthew, I smell you. I do. I'm just telling you right now. I think I smell it on you, so I'm just letting you know there. Okay, the next one, we got our y hat equals 10 plus 0.9x, okay? Carla scored a 95 on the first test. What is the predicted value of her score on the final exam? So what does that mean? Okay, so does the first test explain my final exam? So my first test would be for X, and my final exam would be my response variable, which would be my predicted, which is Y, right? So if I plug 95 in for X, 95 times 0.9, okay? And when I do that, I get my expected value, kind of just put it right here, should be 95.5, okay? So 95.5 is my predicted value, okay? And I keep saying expected. If I'm going to say expected one more time, I'm going to, this is predicted, right? Y hat. Okay, now coming to this one, this is where we have Y expect the value that is given, and here's the value that's predicted, right? This one says on the final exam, Carla scored a 98. So her final exam, again, is the Y, right? That is the Y. That's what she got. That's her value that's set in stone. What is the value of her residual? Okay, so on the final exam, so coming back to this problem up here, she scored a 95 on the first test, right? She got 95.5 for her Y hat, okay? Her 98 was Y, okay? If I took Y minus Y hat, I would get what her residual is. So I would take the 98, subtract the 95.5. When I do that, I should get a value of positive 2.5. So again, remember the Y minus Y hat's the residual. It's a big deal going forward, okay? All right, hopefully this makes sense. Remember, if I was to find the slope here, and again, these have hats on them, so it makes a lot more sense. The A value, or if I had my equation AX plus B, just to kind of go over this again, to find my slope, I do R times S of Y over S of X. Heads up, remember too, I think that this is on your formula sheet. It might be easier and quicker if you just kind of memorize it and say, oh, that's what it would be there. And I say that, and I'm trying to remember what, yeah, okay, I was right. y hat, or y, not y hat, y mean, the mean of y, minus the slope times the mean of x. So with both of these, we just plug in those values to get what the slope is, right? And to get what the y-intercept is. What's cool is we could just find what the slope is, really. Once I find what the slope would be here, I think I could just figure that out by saying, oh, it's this one or that one or whatever, and just plug it in and go from there, okay? Okay, on this one, this is the one where I just want to kind of review this, okay? Here's a good one here. Okay, I'm going to pull up my calculator here. Yes, this is perfect. Okay, I do want to pull this up really fast just to kind of have you see it a little bit. So if I was to put in my data here, right? And by the way, I would, I'm fine with you doing this. Like, I'm fine with you plugging it in. Just be sure if it's a really long one, don't waste too much time. Like that, the mini tabs on the FRQs, that's what they're there for, so you don't have to go through and plug each value in monotonously through that, okay? The water temperature, does that explain the fish activity? So what we're going to do is we're going to put water temperature as L1. So I'm going to put L1 as 21. Let me go here, 21, 4, 29. I just want to just rep this out for you in case you do have a question on it. 18, 29, 22, and 20, okay? 82, 65, 62, 90, 51, 79. I don't know why I'm talking about these right here. There you go. Okay, so I want to play Dora the Explorer. I want you to yell out, what would I do next to figure out how I could go and graph it? Ooh, I hear a lot of you. Just yell it across your house. Nicely done. We want to make sure this plot 1 is on. That's check 1. If it's not on, we press enter and go over here and just make sure that's on. We're going to go to graph. If you can't see it, like mine here, you might have to go to zoom. And what's nice is we know we go straight to zoom stat, okay? So we've got a negative correlation that's here. Fairly strong, it seems like. Yeah, fairly strong. And it's in the negative. It's a negative linear relationship, right? And I don't see any outliers. Maybe this one possibly. I would still say no. So again, what is this showing? Well, first off, let me also go to this. To go to calculate, you can also go to stat, calculate, go down to linear regression, ax plus b. You can use the linear regression a plus bx. Does not matter on that one. When I go to this, make sure L1 is x, L2 is y. Press calculate, and there you are. There's the a, the slope, b, the y-intercept, r squared, which is the variation, right, of the y, of the variation of how okay, let me say this again. The variation of y on the least squares regression line as it relates to the explanatory variable, okay? That was good. So if you need to go back on that, let me say that again. R squared is the coefficient of determination. It is, in interpreting it, it is the variation of y on the least squared regression line as it relates to the explanatory variable, okay? And again, R right here, you'll see that that's negative. Notice R squared is always positive because if I square it, right, it's always positive. So it doesn't tell me really a negative or positive relationship. It just talks to me about the variation of y on the least squared regression line. And I would use context there if need be. Another thing we can just go over with the calculator is if I go to stat edit, and if I go up to L3, I can go back to stat. I'm sorry, second stat, which is our list. And then I go just down to residual. And then what I can do is press enter. And then that gives me my residuals of the, does everything for me. So if you need to do that, you can absolutely do that there as well. A heads up too, if you ever need a residual plot, you can always go to the plot again, except this time I would go instead not to L2. We would have the explanatory as L1. If I wanted a residual plot, I'd just go to L3. Okay, press graph, go to zoom, go to stat, and there you go. There's your residual plot. And all I did was take the stat edit, which was L3, and all I did was on that stat plot, I just put that on as the Y list, right? So if you remember, the X list, the explanatory stays the same, but in a residual plot, the Y list changes to L3, okay? Hope that's helpful there. Man, we are rolling. We're getting a lot done, y'all. I'm hoping this is really helpful for you. Okay, so we've got that. We talked about that. We didn't talk about this. This says increase in the water temperature causes the fish to swim faster. I don't think that that's right. I thought we said that was correct, but I don't think that is correct. Oh, this is as water temperatures decrease, the levels of fish activity decrease somewhat constantly. I would say it was C. I think we said C. Okay, I know it's not there. If you explain this water temperature. Okay, can't explain, right? It's not a cause and effect here. Just a heads up. It's correlation. So we can throw out A. I think I said B in class when I went too fast there. But as the water temperature decreases, right? Because this, if you look at the plot, right? It went like this. And so as this decreases here, the fish activity would increase on that. Check me on that if you have a question or if you want to ask me that tomorrow. If I'm wrong, let me know. Okay, so we've got negative 0.40 is when both measures are, okay, researchers find the correlation. All right, so this is our R. What it says is what percent of the variation in greed can be explained by the relationship with superciliousness. Okay, so in the percent on the Y can be explained by this linear relationship or the least squared regression line in regards to X, right? That's really what we're saying. So we can do R squared by taking this value and squaring it. And when I do that, I should get 60. Well, I just messed up. Yeah, B should be 16% on that when we square it there. All right, what percentage? Here we go. This is another one. So R is 0.63, something like that, right? 63. What percent of the variation, okay? What percent of the variation in GPAs, remember in Y, can be explained? Usually I put least squared regression line. What percentage of the variation in GPAs can be explained by the least squared regression line in relation to the SAT scores, right? And again, that's how I say it. So I got my variation of Y relating to the least squared regression line as it relates to the explanatory variable, or the, in this case, SAT scores. So if this is R, I would square both sides. And when I do that, I would get 39.9%, okay? I think we did pretty good on that in class. What does the square of the correlation mean? Oh, this is what I was looking for earlier, R squared. It's not the slope. Nope. Is it the intercept? Nope. Is it the extent to which cause and effect? Nope. Linear scatter plots can't have cause and effect. The fraction of the variation in the values of Y that is explained by the least squared regression line on the other, or explained by the least squared regression line on the explanatory variable, right? That's really what that is there. The fraction, you could also put percent, right? So you could say whether it's 66%, 7, whatever, whatever percent of the variation in the values of Y can be explained by the least squared regression line of the explanatory variable. Again, hopefully I'm saying it more enough that it's starting to stick. In regression, the residuals are which of the following? They're factors unexplained by the data. That's incorrect. The difference between the observed response. First of all, if I see residual and it asks what it is, put this down, right? Y minus Y hat. Because if I then say it's the difference between the observed response and the value predicted, so this is the observed, this is the predicted, we know that B would be correct, right? No, it's not unexplored. No, it's not recorded after an investigation. Okay, so next one. All but one of the following contains a blunder. Which statement is correct? Okay, We found a high correlation. First off, you can't have 1.09, so we can't have that there. We found a correlation of R equals negative 0.63 between gender and political party preference. Problem: is gender quantitative? Is political party quantitative? No. In order to have this, we must have two quantitative measures. Okay, two quantitative measures. So E is incorrect. Okay. All right. Yes. I can't explain the mini tab. I think I did already, but I can go back to that. Let me do this one and then I'll go to that one. Okay. V, thank you for putting that there. That's a really good question. Keep them coming. Keep them flying. Okay. I know this is going a little bit later, but we'll keep rolling. There's a correlation of 0.54 between the position a football player plays and their weight. We might come back to that. That one might be good. The correlation between planting rate and yield of corn was found to be R equals 0.23, okay? The correlation, so we've really narrowed it down to 3 of these, okay? So let's talk about this. First of all, the position a football player plays. That's quarterback, running back. This right here, I can't. It sounded good, but I can't. Weight is quantitative, but categorical is position, so A is no bueno. Planting rate and yield of corn, we can measure those. Gas mileage and car weight, okay? I like it. So let's say that as we go through this, you could probably see, let's take a look at R. R has 0.23 and R has 0.71. Notice this miles per gallon. R does not have, so if I have like 0.23, it does not have a label on the end of it. R stands alone, right? It explains the DOFs of the actual scatter plot, right? The strength of it, right? Really goes into the strength of it. So I would say that C is incorrect. The B is the only one that could possibly be correct there. All right, this talks about a least squared regression line. This fit, you see a residual plot like this, right? Follows kind of a pattern here. Talks about, is the evidence inconclusive in regards to this pattern? Tells you about the linear model. I'm going to cross that out. The residual plot confirms the linearity of the fuel. No, remember, if it's a residual plot, it would be scattered all over, right? The residual plot does not confirm the linearity of the data. I might come back to that. The residual plot clearly contradicts the linearity of the data. This, I can't say that because of this, I can't do a least squared regression line, right? I can't say, oh, because of that, I can't. But what I can do is say that it provides pretty good evidence that it doesn't confirm it, right? We can't say it contradicts, but we can say, yeah, it doesn't confirm that, right? It does not confirm. We can't say, no, it's not, but we can say, you know, as I look at it, it doesn't confirm that the linearity of this data, okay? Next one, data set A of XY has a correlation coefficient of this, and a second data set B has a correlation of this. Then what? The points in A exhibit a stronger linear association than B. That's false, right? What does R positive 0.65 mean? It means it's going this way. Remember our activity at the beginning when we talked about offensive and defensive points per game? We talked about how in -6 or -0.65 that it would go in the negative direction. So that doesn't mean that they're stronger. So we were just going to cross out A. Now, if one was like 0.9, the other one was -0.6, we could maybe say that. B says the points in B exhibit a stronger linear association than A. Again, they're the exact same, right? 0.65, except one's going positive, one's negative. Neither A nor B has a stronger linear association. Okay? D says you can't tell which data set has a stronger linear association without using the data or seeing scatter plots. That's incorrect because the R does talk about the strength, right? I would say that neither has a stronger linear relationship or association because both of them are the exact same, just one's positive and one's negative, okay? What are resistant? Well, I'll tell you right now. As I look at least squared regression line and correlation coefficient, what are resistant? What does that mean? Well, if I have this value, right, the scatter plot, and I say that R equals 0.8, if I put an outlier down here, what will happen to this R? This R would then, it would decrease, right? It would probably go to maybe like 0.58 or 0.68 or something like that. So this outlier has an effect on 0.8. So we say it's not resistant. It can't just resist this outlier. It actually is affected by it, and it's actually A and B. So actually, the answer would be C here. They're both not I'm sorry. I changed it. If I changed it, you'd be right. Neither are resistant, right? Neither the least squared line nor the correlation coefficient are resistant, okay? Because it's not resistant to an outlier, all right? Oh, man, we went through a ton, y'all. Wow, wow, wow. We're going to go over Minitab here to finish us off. If you have another question, we'll wrap up with this. I think I did explain the Minitab. All I was trying to do here was, if I were to give this data, what can I cross off? Well, the SE coefficient you can cross off, the T, the P you could cross off. What do we need? Well, we know the S is the residual standard deviation, okay? Remember, we can't find the average of the residuals, right? Because that would be 0. So we say that this is the standard deviation. We use the standard deviation for finding the average error each value has, or average residual each value has to the least squared regression line, right? Which is the y minus y hat, observed minus predicted. R squared we'll need, right? That's very important. We can use that to also go to R, right? It's very important. Make sure we put that in a decimal when we go to R. R squared ADJ, don't worry about. This right here is probably the most important. The constant, think of constant as the value by itself, right? This is if I had y hat equals ax plus b. B is the value by itself, so this would be 109.87 in for B. And the h would be our x, our explanatory variable. And our explanatory variable we'd put for A, negative 1.13, okay? So we would use that, right? We plug this in to say y hat equals negative 1.13 x plus 109.87. In context, I would really like you to say that negative 1.13 times age and then plus 109.87, and that equals score hat, right? Or the predicted score. I like that a lot. That right there is really helpful to me in determining context. Sometimes I can even give you some context if you forget or if you don't do a good job of it. So this is a big deal here. Remember, if I plug in my daughter's age when she said her first word, which was 10 months, I can get a predicted value or score that she'll get on here. Now, her actual score may be different, and when I find her predicted and her observed score, that's when I subtract to find what my residual is. I average up all the we average up all the residuals by finding the standard deviation. We can't average them up because it would be 0. And hopefully that's making sense there going forward. This is Coach Jay signing out. I hope you y'all had a good time tonight. Man, I tell you, that was a podcast and a half. The longest podcast Coach Jay has ever done. Can you believe that? It's Coach Jay signing out. If I hit one more, I swear to you, I'm going nuts. Oh, that was pretty close, y'all. Hey, see y'all. Hey, I love y'all. Let's dominate this test. See ya. Bye.